Hello, myself Naveen Kumar Saini. In the course Wireless and Mobile Communication, today we are going to discuss about the multi-carrier modulation. So one thing which is keep in mind about the modulation, the basic concept about the modulation is what? Where we modulate the modulate the message signal with the help of the carrier signal. So this is a basic definition of the modulation, which we have already gone through in our previous lectures. In which we have modulated the BPSK, QPSK, this type of basic digital modulation techniques are there. So in our wireless communication, we will discuss about the multi-carrier modulation. So here we will discuss about the basic principle of orthogonality, which is used for the multi-carrier modulation, and in that we will discuss different modulation techniques which is for the multi-carrier. Then another interference reduction methods where we will discuss about the zero intersymbol interference, and some communication techniques which we are going to discuss about that, which is used to mitigate the ISI or intersymbol interference. So in that, as we have already discussed about the digital transmission techniques in the previous lectures, where we used to mitigate the ISI intersymbol interference. So here the first thing which is important to know about digital transmission, which is used to transmit through the band limited channels, and these band limited channels are main cause for the ISI or intersymbol interference, and this ISI occurs because of the overlapping of the symbols. So this intersymbol interference is caused in this band limited channels, which is wide band in nature. So what is solution for that? So solution for this one is to reduce this wide band into the narrow band signals. Okay, so if we talk about this ISI reduction techniques, so one of the method for reduction of the ISI is the equalizer. So by using the equalizer, we can reduce the intersymbol interference or the ISI. So this is one of the method we generally we use it. Okay, so another alternate approach for reduction of ISI is to design the bandwidth efficient communication system. So in the presence of channel distortion, which is nothing but this is the fading effect, or equivalently ISI, which is divided the available channel bandwidth into the number of equal bandwidth sub channels, or for these sub channels we use the sub carriers. So where the bandwidth of each channel is sufficiently narrow. So as we said, this multi-carrier modulation is used to convert this wide band to the narrow band. Okay, so if we have a wide band, so in that case the ISI will be more, right? But in the case of the narrow band, ISI can be mitigate, or we can reduce the ISI in the system. So there are two main methods for reduction of the ISI. First one is using the channel equalizer or the channel filters or adaptive filters at the receiver side, or second method is to convert the wide band system into the narrow band system. So for reduction of the ISI. So a basic diagram of multi-carrier modulation technique is there, where we have this data. So this is the data stream which we have to transmit. So this data stream can be of 0, 1, 1, 1 like that. So these data streams we have to transmit. So in the first way to convert this serial to parallel means, so this data stream which is coming from the transmitter side, so it will be transmitted in the parallel methods, like this M1 bit is the first channel, M2 bit is the second channel, and so on. Means if we are transmitting the 1 0 1 1 0, so it means this maybe one method is we are using single bits at a time like this one, right? So this is the one method. Second can be we are combining the bits and we are transmitting, like we are transmitting 1 0 from here, or we are transmitting 0 1 from here, and so on, right? So there are different methods or different modulation techniques for using the multiple channels to transmit the same signals. Okay, so the method for this one is called the OFDM, which is the orthogonal frequency division multiplexing. So in that case, basically what happen? So we use the different subcarriers, right? So as we know, in the digital communication system, we use the one carrier for transmitting the one of the by using the different one modulation technique, that is the BPSK or QPSK. But when we talk about the OFDM, so in this case what happen, we transmit the same signals by using the different subcarriers, right? So when we are using the M1 bits, so this M1 bit will be modulated by the frequency F1. When we have the M2 bits, so these M2 bits are transmitted by or modulated with the help of the carrier F2 and so on. It means from F1 to Fk we have the k number of subcarriers, right? So this complete wideband is divided into the different subbands. So the frequency for that one is F1, F2, F3 and Fk. So the bits which are transmitting, so this will be modulated one bit by bit from here, like 0, 1, 1, 0, 1. So it means this 0 will be modulated with the frequency F1, this 1 will be modulated with the frequency F2 and so on. So this conversion of wide band to the narrow band can be takes place by the OFDM concept. So in this OFDM concept, which utilizes the passing of the input data bits stream into the M symbol streams, right? And each with the symbol rate, that rate is this is a rate for the transmitting of the signals, that is 1 upon Ts, and each of which is in turn used to modulate the parallel synchronous subcarriers. So this is nothing but the parallel synchronous subcarriers. So these subcarriers can be synchronized at the same clock. Okay, so so that we can modulate the bits, every bits by these different subcarriers. So with an OFDM system which is having the M subcarrier channels, right? So just like this is F1 frequencies for the one channel, F2 frequencies for the second channel, F3 frequency for the next frequency for the next channel and so on. Just like Fk frequencies for the Fk this kth channel, right? So in that way, if we have n number of subcarriers, means n number of channels can be utilized. If we have the capital N number of or the k number of subcarriers, in that case k channels can be utilized. So in that, the symbol rate on each subcarriers is reduced by the factor of 1 upon n, right, which is related to the symbol rate or a single carrier system that employs the entire bandwidth W and transmits the data at the same rate as the OFDM. So in this case, when we modulate these different bits like F1, F2 and so on, so here this will be the one modulated signal, this one will be the second modulated signal and so on, that is the kth modulated signal. And after that we combine all these modulated signals by this using the summer, right? So this is nothing but the summer. So this summer will add on all the modulated bits and this a combined signal is called the one OFDM symbol. Okay. So this modulation can be your BPSK signal modulation or the QPSK signal modulation. So based on this different subcarriers, the different digital modulation techniques can be used for the modulation. So when we combine all these modulated signals at the summer, so in that case the resultant will be a only one OFDM symbol. So resultant we can call it as the one OFDMA symbol. I hope this point is clear to each one of you. Okay, right. So this is principle of orthogonality. So one of the major effect of multi-carrier modulation is we have to use the frequencies or the different frequencies with the which follows the orthogonality. Orthogonality means the null points will be cross over to each other, right? null point of every frequency spectrum must be crossover to each other. So in that case the overlapping can be avoided. When the overlapping is not there, so in that case the ISI can be reduced. So this is the effect of that. So some properties we will discuss about this in when we talk about the principle of orthogonality. So in that case, first thing is the two periodic signals. This is an example for that. Two periodic signals which are orthogonal. So when the integral of their product over a period equal to the 0, right? So in this case we can see when we have two continuous time signals. So frequency is f0 and we have nth and the mth signal. So in that case when we take into the one time period 0 to t, then the product must be 0. So this is the case in the case of the continuous time. So when we have a discrete time signal, so in that case in the discrete time we use this type of notation for that. So when we combine or multiply these two signals, so in that case the resultant must be also 0, right? So this is the two condition, these are conditions for the which follows the orthogonality. So in the spectrum we can also see when we have the signal here which is a rect signal. So in when we combine it with the delayed version of this signal, so what happen, we can see this is one spectrum, this is the second spectrum. So the null point of this first spectrum will cross the null point of the second spectrum. So this is the point at which the null point occurs and the crossover is there, and at this point we see when there is a null point is there, in that case the overlapping is reduced, or which follows the orthogonality principle, right? So it follows the orthogonality principle. So if this crossover point is somewhere shifted, so in that case the overlapping will occur, just like if you are showing like this and this one is like this one. So this will be your intersection, and so in this case this overlapping will be there. So this will cause the ISI, right? So that is why the orthogonality must be followed, so that this must be cross to at the null point. Okay, so this is the nothing but null point. So I hope this point is clear to all of you, right? So this orthogonality principle must be followed into the multi-carrier modulation technique. Okay, so another representation of the same when we talk about the principle principle of the orthogonality principle. So we see f1 is the frequency subcarrier frequency 1, this one is for the f2. So we see this is the one waveform for the modulated signal of f1. This is the second waveform of the modulating by the frequency f2. This one is f3, f4, right? So in the frequency domain, when we combine all these four frequencies signals f1, f2, f3, f4, so this combined, this is the four subcarriers, right? These are four subcarriers. Suppose we have the so much subcarriers. So out of these so much subcarriers, we are using the four subcarriers, and these are the respective modulated signals. And when we combine, then the combined result will be like this one in the time domain, right? So when we combine it, then in that case we see that these are delayed version, right? So this is the f1 frequency subcarrier, f2, f3 and f4. So all these things we have to see the null point is there. So when the null point is there everywhere, okay, so when the null point is there, it means there is a this is nothing but the ISI is 0 in this case. So we can write for this case that is the ISI is 0. So in the multi-carrier modulation, the null point crossover must be there, and which affect the 0 ISI or the mitigating the ISI. So we can also say this thing as the mitigation of ISI, and sometimes we call it as the reduction of ISI. So prime important factor for the multi-carrier modulation, that like the OFDM, that is follows the orthogonality principle. Okay, so when we have again the four subcarriers, and previously we were talking about the 1 bit, Now when we talk about the multiple bit or the multiple symbols, so we see this S1, S2, S3, these are the three subcarrier, these are three symbols which are modulated by the frequency F1. Okay, so we see here, and similarly this symbol F, S4, S5 and S6, which is modulated with the frequency F2, and S7, 8 and 9 modulated with the frequency F3, 10, 11 and 12, these are symbols which are modulated with the frequency F4. So more number of symbols can be modulated by the these subcarriers, and when we combine these subcarriers, so we can see here in this diagram, just like in the previous case, S1, S2, S3, which is modulated by the frequency F1. So this S1, S2, S3 is modulated with the frequency F1. So this is a spectrum for that. S4, S5, S6 modulated with the frequency F2. This is a spectrum for that. S7, 8 and 9 is modulated with the frequency F3. So the spectrum is for this one, and the last S10, 11 and 12. So this is modulated with the frequency F4. So this is the spectrum for this one. So these are 4 spectrum which we are getting. Okay. So we see here, just like in the whole bits or symbols, we divided this. We are divided the. We are taking the window of the first 3 symbols and then second 3 symbols and so on. So these are modified or the modulated with the different frequencies. So in the parallel fashion, we see this is nothing but the one OFDM symbol. This is nothing but the one OFDM symbol. So this symbol period is nothing but this is the TS. So TS is equal to 1 divided by delta F. So delta F is nothing but this is the spacing between the 2 subcarriers. So this is the delta F, right? This is the delta F, which is nothing but this is the spacing between the 2 subcarriers, delta F, right? So in here the concept of carrier frequency allocation to the symbols, which is defined here. Serial to parallel conversion, first step is there, and then mapping into the frequency domain component after the modulation. So in that way, the first is the we have to convert the serial to parallel converter, and then we have to use the mapping into the frequency domain, right? So in this way, this basic principle of orthogonality work. So in that symbol period for the OFDM is nothing but total symbol period will be n times of the T OFDM. So in that case, we see if the modulation scheme which is used on the ith subcarriers, which can accommodate the k1 bits per symbol, and the subcarriers are spaced by 1 upon Ts, right? Subcarriers are spaced, that is 1 upon Ts or the delta F, where Ts is the symbol duration of the subcarrier. So this delta F is the symbol space, frequency space, spacing between subcarriers. Then it can be followed the orthogonality principle. Then the T OFDM, the symbol duration of the OFDM symbol, and Ts is the symbol duration of the subcarriers, which can be related by the formula Ts is equal to n times of T OFDM. Okay. So in that, when we define the value of n, or we use the value of n, which is can be very sufficiently large, in that case the symbol period can be significantly larger as compared to the time duration of the channel time dispersion. Okay. So in this case, the ISI can be made arbitrarily very small by the selecting value of n. So this value of n is more important thing to reduce the ISI. We cannot take the n is very large, or we cannot take the n is very small. So in that way, this value of n can be defined for the defining the using the subcarriers and to reduce the ISI, inter-symbol interference. So in this case, when we maintain the time synchronization among the subcarriers, then OFDM allows us to transmit a different number of bits per symbols on each subcarriers, right? So here subcarriers that can have a higher SNR value or signal to noise ratio, due to a lower attenuation, it can be modulated to carry the more bits per symbol, right, than the subchannels that yields a lower SNR. So what is the meaning of that? Basically, for using the high modulation techniques in the for generating the OFDM symbol, which can give the more high SNR. So when we have the high SNR, in that case the data rate number of bits are more in a given symbol and the data rate will be high. So that is why the OFDM transmission, by using the OFDM transmission, data rate must be very high, right. So that is very important. So here the concept which is used for DFT and IDFT implementation for using the OFDM. So basic concept behind the OFDM symbol is by using the DFT and the IDFT. So this IDFT is used at the transmitting side and DFT phenomena is used at the receiving side. So which I am assuming that each one of you know about this prerequisite of the DFT and IDFT for the course of wireless communication, which is very important. In your third year you have already gone through this concept for the DFT and IDFT. So as I had told you, at the transmitting side we use the IDFT concept for transmitting, making the serial to parallel conversion, and then parallel to serial conversion at the receiver side we use the DFT modulation techniques. So here it is representing that first is the data, and then we have second block is the serial to parallel converter, and then we use the IDFT, and then we use the D2A converter, and then channel is there which is the wireless in nature. Then opposite of this concept will be there, analog to digital, and then DFT. So we are using the DFT at the receiver side, then parallel to serial conversion, and so on. This is the estimated data. Suppose the data which was transmitted S, and the estimated data must be S cap. So we have to reduce, we have to minimize the S minus S cap, right. So we have to minimize it. So this is the error which we have to minimize for reducing the ISI. So I hope these things are very much clear to all of you, how we use the OFDM system, or what is the orthogonality principle. In the next lecture we will discuss reduction techniques of the OFDM system, and then we will also go through the LTE system, right. Thank you very much.